Hello participants, I welcome all of you for this short-term training program on applications of MATLAB in mathematics, science and engineering. I am Dr. Dinesh Wankhede, Assistant Professor, Electrical Engineering Department of St. Vincent Pallotti College of Engineering and Technology, Nagpur. I will be delivering this session on the topic of power electronics. That means application of MATLAB in power electronics domain. So let us start with my presentation. These are the contents of my presentation. I will be covering following points during this presentation. Simple circuit diagram related to power electronics. Uh, I think three-phase SPWM inverter is a good choice for this particular circuit. This particular project will simulation will help us to get the nitty-gritties of the Simulink model, MATLAB Simulink model for our power electronics module, power electronics domain properly. Second thing is, as we have selected SPWM inverter, and this particular STTP is for beginners and starters. So I would be explaining concept of PWM, SPWM in brief before proceeding for inverter, and with some assumptions that beginners are a little bit conversant with the bioelectronics concepts. Third point of the content is Simulink model of three-phase SPWM inverter with R load. So we have selected R load, we have selected SPWM inverter, three-phase SPWM inverter with R load, and we'll be preparing a Simulink model for the same, and we'll be discussing few outputs. We will be observing, we will be studying few outputs with the resistive load. Fourth point in my presentation will be components required to accomplish the simulation of three-phase SPWM inverter. So as we have selected this particular circuit diagram, we will be simulating this particular circuit diagram of three-phase SPWM inverter with R load. So that simulating model needs lot of components. So I will be giving explanation for all components. I will be presenting you with the list of components first, and I will be explaining you all components in detail. Fifth point of my contents are targeted outputs. So which are they? So we are targeting waveforms of line voltage and phase voltage. We are limiting ourselves with the voltage waveforms only. This is as we are just starters, we are beginners for this particular module, power electronics module. I thought it will be a good choice to limit ourselves only up to line and phase voltages. And last point of our this module, power electronics module, is FFT analysis of our targeted outputs. So how to get harmonic analysis, or FFT analysis gives us the harmonic spectrum. So how to get insight of these harmonic contents of the targeted outputs, that means line voltage and phase voltage waveforms, uh, that will be covered. in this particular module. So let us start with the first point. So my dear friends, this is our circuit diagram which we are going to simulate. So as this is a circuit diagram, and um, there will be a difference. There is a difference between circuit diagram and Simulink model. So this circuit diagram, schematic diagram, is the one which we study while in the classroom, theory classes or lectures, during lectures, or preparing ourselves for exams, theory exams. But this is only the idea. Simulink model looks a little bit different than this particular circuit diagram. So this circuit diagram contains VDC, then there are 6 switches, right? I will be giving a brief introduction of this circuit diagram, brief explanation for the circuit diagram, and then we'll move ahead. And resistive load is connected, right? Resistance of equal value, and it is neutral, that means star connected, right? And please observe this: S1 is here, S3 is here, S5 is here. So we can give any numbering, but there is a particular type of numbering we follow in power electronics. So this is the circuit diagram. VA, VB, VC, and these are the um, voltages for this particular legs. So this is leg 1, this is one leg, second leg, and third leg. So this is a little bit introduction of explanation of our circuit diagram. Let us move ahead. uh, Before starting with the next points, I thought it will be a good idea to understand what is meant by PWM or SPWM. In brief, this will be a short introduction to the concept of SPWM for the students, for the participants who are new for the power electronics area. So uh, I will be trying only to give important idea, important information which will help us to understand this particular session, concept of this particular sessions well. So here it is a sinusoidal waveform. You are looking here, you must be aware of. And this is a triangular waveform. So triangular waveform is called as carrier waveform, and sinusoidal waveform is called as desired waveform or reference waveform or modulation waveform. So our modulation waveform is sinusoidal, and carrier waveform is triangular waveform. So we can have different types of the carrier waveform. Here we have it is shown triangular waveform as a carrier waveform, carrier signal, but we can go for trapezoidal also, sawtooth also. Any kind of waveform we can treat as a carrier signal, but studies shows that this is triangular waveform is one of the best. So there is PWM, my dear participants. PWM itself is a very vast area. So uh, this particular sinusoidal waveform, say it is having 50 hertz frequency. So carrier waveform, carrier signal will have more frequency than the modulation waveform. So generally we keep it as 1000 or 2000 or 4000 hertz frequency for the triangular waveform, so that it crosses the sinusoidal waveform uh, at different points. So this is going, say this is crossing at this particular point, right here and here, and from this point to this point. So we are having this much um, width of the pulse. This is the width of the pulse which is created by crossing over of triangular waveform with the sinusoidal waveform here, and pulse width is defined here, right? Similarly, we can go for any other example, any other crossing of the triangular waveform with the sinusoidal waveform. Here the pulse width is very small. Here again the pulse width increases. Here again the pulse width increases. So what we are observing here is pulse width varies. Pulse width from this point, right, from this point to this point, every there are number of pulses, and these are the pulses with different pulse width. They are not having same pulse width. And what is the use of having pulses of different widths? They are ultimately going to affect harmonic contents of the output voltage waveform and current waveform, be it line voltage or phase voltage. So the study shows that if we compare the sinusoidal waveform with the triangular waveform, whatever pulses we get, those pulses gives us one of the best harmonic content in the output waveforms, output parameters like line voltage, phase voltage, or currents also. So moving ahead, so similarly we can have three phase sinusoidal waveforms here. It is shown here that R phase, this is R phase, this is peak of the Y phase, sorry, B phase, A, B, and C, and this is the peak of the C phase, that means RYB. And similarly, a triangular waveform is treated as a carrier waveform, and we get different pulses here, and with the different pulse widths, different widths, so as we can get the harmonics removed from the output line voltage or phase voltage waveforms. And we are going to use this technique now. We are going to use this technique in our simulations. So how to achieve this? This is the interesting part of this. So we are ready with the Simulink model. Of course, I will be connecting each and every component of this particular Simulink model soon, but before going for that, I will be explaining these components to you. So this is sinusoidal waveform of R phase, Y phase, and B phase. So with some proper um, values inserted in this particular blocks of sinusoidal waveforms, we can achieve three phase waveforms with 120 degree uh, with 120 degree phase shift. Once they are created, we can observe whether our output is correct or not by connecting scope here. This is mux, which multiplexes these three waveforms, and we can see all the three waveforms here in scope um, with this kind of connection. And then this is important, we are generating carrier waveform. We are generating carrier waveform here, and we have to uh, insert some values here to generate the carrier waveform of desired frequency. So these all RYB sinusoidal waveforms are of 50 Hertz frequency, fundamental frequency right? And this we can have 2000 or 4000 hertz frequency. So whether our carrier waveform is properly generated or not, we can observe it here in this scope. Then these sinusoidal waveforms of RYB and carrier waveforms are summed up here, and then they are compared here, and our signals are ready here. So S1, S3 and S5 are the signals. So we call these signals as a gate pulses. So gate pulses are ready here, and we can observe these gate pulses here in the scope. So everything is observed, tested okay by observing all these waveforms in the scope properly. Once it is through, then these particular gate pulses are ready to fire the IGBTs, that are connected here in the bridge circuit of the inverter. So this is called as power circuit. This particular block is having power circuit, and remaining other than this particular block, all this particular circuit is called as control circuit. So we are in the next slide, we are going to see the inverter with the power circuit. So this is our inverter with the power circuit, and uh, these are our gate pulses. So these are our IGBTs. There are 6 IGBTs, right? And uh, we know that we cannot have uh, both the IGBTs in the one leg. So this is our leg number 1, this is our leg number 2, this is our leg number 3. So we cannot have both the IGBTs of one leg. That means these two IGBTs cannot be on at the same time. Similarly, these two IGBTs cannot be on at the same time, and similarly in this phase third leg we cannot have this IGBTs turned on at the same time, because otherwise it will create a short circuit. So we can have this IGBT on, at the same time this will be off. Similarly, if we have this IGBT on, this will be kept off, and similarly if we are having this IGBT on, we have to keep this particular IGBT off. So that is achieved by using NOT operator, logical operator. So by using this NOT operator, we have created another set of another 3 gate pulses for this particular IGBTs. Then we have connected a resistive load, R load here, 3 phase R load, neutral is there connected, that means star connected load. And with this kind of arrangement, this kind of voltage measurement blocks, we are measuring line voltages. This is measurement of line voltage, this is measurement of phase voltage. So we are having line voltage and phase voltage measured over here. So this is basic Simulink model. This is basic Simulink model. This is IGBT, and IGBT is having cathode, anode, gate, and this 4 terminal. Here we have connected terminator. This terminal is not useful right now, so we have connected a terminator port here at this port, and uh, that port is completed, right? So this is all about our Simulink model. Now I will take you through the components required to create this particular Simulink model in our next slide. So what we need DC voltage source, then we need power devices, that means switches. So we have selected IGBTs. You may select IGBT, MOSFET, SCR, GTO, anything of your choice. Then we need to create a reference waveform. So sinusoidal waveforms are needed. How to create it I will explain in the tutorial part. Mm, Scopes we need, always we need scope to check whether our reference waveform or carrier waveforms or gate pulses are correct or not. So next we need carrier waveform. We have selected triangular waveform. Remember, carrier waveform will be having higher frequency um, than reference waveform, sufficiently higher frequency than the reference waveform. Our reference waveform will have fundamental frequency, that means 50 Hertz. Carrier waveform will have around 4000 Hertz frequency. Then summation block, then we need compare to constant block, comparator, then we need go to block, then we need from block, then we need logical operator not, then we need terminator, then we need voltage measurement also. All these blocks are shown you in the Simulink model. Then we need mux, then we need gate pulses. Gate pulses are created from sinusoidal waveform and triangular waveform, of course. And then we need three phase R load, and then we need power GUI to get the FFT analysis also. So just again, this was the list, and I will take you one by one with the details of the components these are required. So uh, these are the block parameters of all. I will be taking you through the block parameters of all the components, um, so that you can have some idea before going for the exact tutorial. This is DC voltage. We can have amplitude here. Amplitude here is 100. So we can have any amplitude here. We can have any amplitude inserted here, right? Then this is our IGBT. These are the block parameters of IGBT. This is our sinusoidal waveform, reference waveform. So we have to take care of frequency here and phase also. Frequency as well as phase, because there are three phases, so we need to maintain 120-degree phase difference. This is sinusoidal waveform. Then we need scope. While handling scope, we need to understand how the settings. This is a setting block, parameters block, and this there are three important parameters: general, history, and style. So we will see while in the during the tutorial, exact hands-on simulation. I will show you with the help of proper MATLAB software how to do it, how to set the parameters of the scope. Then this is important, this is repeating sequence, and right now you must be seeing that this is a sawtooth type of repeating sequence. So these time values are important and these output values are also important. That means at time 0 we are having output 0, so at time 0 we are having output 0, and at the time 2 2 seconds or whatever 2, we are having output 2. So this must be the 2, this must be the 1, this must be the 2, and by inserting this, by fixing these values for the output and time, we can get this kind of repeating sequence, right? So entering time values and output values here properly, we can decide any switching frequency, any frequency for the repeating sequence, and any shape also, any shape of the repeating sequence. This is one of the key uh, um, key parameter key parameter in the SPWM simulation. So next is sum. These are the block parameters of summation block. compare to constant, then go to. So go to means this particular function, this particular block, it collects the signal, and then um, this is the from block, it collects the signal from go to and provide it to the next power device. So we are using this one to provide get pulse to the IGBTs. This is logical operator not, just to reverse the gate pulse for the IGBTs in the same leg. This is terminator. This is voltage measurement block. This is mux, so we can have a number of inputs here. So we are using it for 3 inputs in our simulation, and these are the gate pulses. I have shown this particular diagram before. For these gate pulses I have shown it. So we are going to get for 50 Hertz frequency, we are going to get pulses of the different pulse widths, and this was explained by me earlier by using some diagram. So this is actual gate pulse we are going to get, and this is snap of the scope we are going to use gate pulses. So this is our 3-phase load, and you can keep any value here. So right now it is 100 ohms. Basically this is our load is created out of RLC load. We have disabled L and C part of this particular load, so remaining part is only R. So branch type is only R, and this is power GUI, and power GUI is a multi-functionary block, but we are going to use it with the target of FFT analysis. It gives us lot of parameters, lot of things we can assess, analyze. So this is configuration of the parameter, steady state voltage, SN current, initial state setting, most of the many parameters are there. But in our module, power electronics module, we are going to use only FFT. With reference to FFT, we are going to use this particular block, that is power GUI, graphical user interface. So these are the 16 components, and we have already seen the Simulink model also. So get ready for the tutorial on the MATLAB. So we are going to use these 16 components to prepare our Simulink model, and we are going to, after preparing a model, we are going to target these outputs. What are these outputs? Line voltage waveform, phase voltage waveform, and then we are going to get the FFT analysis of the line and phase voltage waveforms. So dear participants, now get ready for hands-on tutorial on the MATLAB. I hope this will help you to start with the small Simulink models. So let us start with the MATLAB model.